postdoc with Marc Ernst. Marc Ernst is a physicist by training who got his doctorate at the Max Planck Institute for Biological Cybernetics in Tübingen, where he worked in Heinrich Bültow's group. He did a postdoc at the University of California in Berkeley, where he did already this form of multisensory integration that we will be talking about today. He then was back for 5 years as a group leader at the Max Planck, where he was responsible for sensory motor process work, both experimental and theoretical. And he's been heading a Max Planck research group since 2007 on multisensory integration. And I just learned that he will be moving to Tübingen, to the new Excellence Cluster for Cognitive Technology next year. So thank you for coming, and we're looking forward to your talk.
Yeah, thanks for the introduction, Gregor. And as the other speakers, does that sound good? For me, that sounds bad. Can you all hear me? Yeah, okay. Yeah, thanks for inviting me here. I'll give another talk on multisensory integration, as you have heard a couple of talks already before. I give also another view on that. Of course, I believe that's the correct view. Okay, so let me start very simple by lining out for those of you who haven't got what multisensory integration is all about. So if you knock somewhere, you get information about the location where I've knocked, from vision, from audition, from proprioception. And at some point in the brain, this sort of information should be integrated into some location. I think even Ernst would agree with that. For the multisensory, you have one representation of location there. Of course, in order to do this, first of all, you have to get the visual, auditory, proprioceptive information into the same coordinates, which may be a highly nonlinear process. But then once you have the three estimates of location, you somehow want to integrate this, and this is the process I will start my talk with. And I want to try to convince you that you do something relatively simple, namely that you do a linear combined weighted average, and the weights will be proportional to the variances that you have in your neural system. You always have noise, and the inverse of the noise is what we call the reliability. So it will be weighted by the reliability of the signals, and that gives you an estimate of the location. Of course, we were not the first one addressing this question. This question is relatively old. One of the famous papers in this field was done by Rock and Victor already in '64. And what they did is they had people look at an object through a distortion lens. And that distortion lens made this cube look like a rectangle. So you created artificially a conflict between the senses, and then they asked basically, what do you perceive? And they did this in multiple ways. They measured, first of all, vision alone, they measured touch alone, and then the interesting cases, of course, are the combined cases where there's a conflict. And they measured, for example, by asking people to draw whatever they perceive. They had a range of objects from which they could match it visually, or they could match it haptically. And if you look at the numbers that come out from that, is here they report the aspect ratios. In physical terms it would be 2, the perceptual terms is 1.9, so it's relatively close to veridical. This square here would be physically 1, perceptually when you draw the aspect ratio that would be 1.98, so also very close to the veridical number. Interestingly, of course, is what happens if you have both sources of information simultaneously available. What people report is a number that is relatively close to what vision alone would tell you, but slightly less, so slightly biased towards the helping modality. Similar, here now they report millimeters. If you look at, I think it was 12 in physical terms, what people perceived was 13.4 millimeters on average. This one I think was 24, so a slight underestimation, but within the error of the physical. And then again, if you do the cross-modal case, what you find is that the cross-modal case is very close to what the visual modality says. And the interesting case is, of course, now what happens if you match that haptically? Would you then find a more haptic bias? And the answer is no. If you do the matching here, you again find, even if you do a haptic matching, a number in the cross-modal case that's relatively close to the visual modality. So from this time on, in the literature there was this term of visual capture. So it means like vision is a dominant sense and you throw away the haptic information more or less. And that's also apparent in other domains, in the visual auditory maintenance about perception. Also there is visual capture. There's another phenomenon where it's more about temporal events. Visual auditory, there was the auditory modality that dominated, so there was auditory capture. So there's other phenomenon of capture. So when I moved to Berkeley, we were basically sitting over these results and we were slightly puzzled because it certainly doesn't make sense for a nervous system, if it once collected information, to throw away information. So the question we ask ourselves is, what would be the optimal way to come up with, to combine sources of information? And we did a very similar experiments as Rock and Victor have done. From the 60s on, the technology is slightly advanced, so we do this all in virtual reality nowadays. So we have people look at a mirror and we render the objects that people see. We use little robot devices called Phantom to render haptic objects where you can feel. The good thing about that is that you can create conflicts no matter what you want because it's all computer controlled. And I can also precisely control, which in this multisensory task is very critical, the timing of when you see something. So here I can really ensure that you see and feel only exactly at the same time. Once you touch the object, I display it visually. Okay, and the task we used was a little bit more, I would say, a thorough psychophysical task. We didn't do a matching or a drawing or whatever. We did two interval force choice discrimination tasks, so we gave them a bunch of objects and they always had to compare two and say which of the two is bigger. And you do this multiple times. For the people who are not from psychophysics, what you get then is a so-called psychometric function, and I'll show you what that will look like. But first, before I come to the results, let me explain what we think is would be an optimal model how you would combine such sources of information. So let's draw the situation again that we have, and that's kept general because we believe that this model is applicable to all sources of information that you would combine. So you have two cues on one axis. In the Rock and Victor, it would be the size of the object, this axis. The two cues are noisy, and of course they have different amounts of noise. If this is the haptic one, it would have more noise than if this is the visual one. As I said, what we define is the reliability. We define this as the inverse of the variance of these sensory channels. And then what you can show mathematically, what is the best way to combine it is to form a weighted average between the two cues where the weights are proportional to the reliability of the information that is there. Why I say it's optimal is because what you end up with is a more reliable, because you have more sources of information, of course at the end you end up with a more reliable estimate. And I guess that's a good goal for the perceptual system at the end, to come up with something that is more reliable than is there, and not throw away information. So what that would predict is, if I go ahead and change the reliability of one of the channels, so make the visual one, for example, here see one more unreliable, so put more noise in it, you should find a reweighting of the information more towards this other channel here. And that's exactly the experiment that we have done. We've used the visual haptic, we introduced the conflicts, and then we added noise to one of the channels, and we looked at how information gets weighted. The way that looks like, so here again we have the size of the object drawn. Here we report a proportion of trials that you see when you do this comparison, the comparison object as being bigger. We introduce this conflict between the visual and the haptic one, and then we measure psychometric functions. And that looks like this. So if there's the comparison object is very much smaller than your standard object, which is created with this conflict, you will never say that your comparison is bigger. If it's much bigger, you will always say it's bigger, so it's 100%. And at some point there's this transition. And exactly at this point where you can't decide, where 50% of your answers say it's bigger or smaller, that's what we call the point of subjective equality, and that's what you perceive. Another property of the psychometric function, which is nice, is the so-called J&D. That's defined, that's a simple matter of definition. We define it at the 84% point because it's a convenient point. you can fit this here as a cumulative Gaussian function, then that is basically representative of the underlying sigma of your Gaussian function that you're having. So here is drawn basically the percept with the Gaussian function, and that maps directly to the psychometric function. Okay, so here's basically the result that Rock and Victor also found, namely if you have visual and haptic information, put them in conflict, what you find as a percept is relatively close to what a visual modality would say. Now the tricks that we did is that we added noise to the visual channel, and then what we predict is a reweighting. And that's exactly what you find. So we add more and more noise, and the more noise you add, the more the psychometric function move towards the haptic modality. The good thing working here with psychophysics is we can do the whole thing quantitative. We can measure the visual channel alone, we can measure the haptic channel alone, we get an estimate of how reliable the visual information alone is, how reliable the haptic information alone is. We can put this in this formula in order to make a prediction, and that is what a prediction is for our case that we have measured. And as you can see, that this prediction pretty much matches with what we have measured in the cross-modal case. We can do also a second prediction, namely what the reliability, or in this case the reliability is simply proportional to the just noticeable difference, what the just noticeable differences would be in an ideal situation. And if we plot those in top of this graph, you can see that this one, this, and this, they match pretty well with what we have found experimentally. So here we have a parameter-free model that completely predicts our integration behavior. And therefore, from this we concluded, and that's the stuff I've done in Berkeley with Marty Banks in 2002, that humans integrate visual and haptic information in a statistical optimal fashion, meaning that the signals are weighting according to the reliability, that the benefit of integration is that it reduces the variance, you get a more reliable percept. What you need in order to get that is some online representation of how reliable the signals are that you're dealing with. And there's some models out there how the brain may deduce from whatever observing the sensory signals, how it may observe how reliable also source of information is. You not only need a representation of the quantity itself, but also of the reliability of the measure. Okay, going back to this, of course this model is very simple. It makes quite a few assumptions, and I want to, in my talk, so this was basically just the introduction, in my talk show you a few examples of what happens if these assumptions are violated, and especially I want to look at what happens if they are violated for a long time, then you get learning behavior. Two of the assumptions that exist is, first of all, that you assume that you know that these sources of information belong together, so there's a signal correspondence there. So you know that they have redundancy in there. The second is, and that's what we have heard from Jörn, is that the signals may be unbiased. That's in this model, it makes the assumption that the source of information should be unbiased. So we are looking at what happens if this assumption is not fulfilled, and this one in a couple of learning experiments that I will show you in a second. Before I go to the experiments, since we have two sensory input channels, it's convenient to look at the entire model or the entire thing in a two-dimensional space. So I'm replotting basically what I've just showed you today in a two-dimensional space. So here we have our input matrix, which is the haptic channel, the visual channel. Here we have this conflicting input between the visual and the haptic. They don't agree. If they would agree, they would lie here on this diagonal line. That's the input. Now, integration basically, well, they are noisy, that's why it's drawn as a Gaussian blob. They have a sigma in the visual and the haptic domain. In this example, they are equally reliable in both modalities. Now, the assumption basically say that we know perfectly that the sources of information are redundant. And we can represent that in a Bayesian framework as a prior. That's our prior knowledge, and we know perfectly that this information should come in truth from this diagonal line. They represent the same object. In this view, that is not allowed that anything off the diagonal would really exist. And if you now simply multiply those two distributions, what you end up, in terms of the Bayesian formula, what you end up with a percept which is coinciding here with the diagonal line, and it has exactly these properties that the variance is smaller by this integration process as the integration. The good thing going here in the two-dimensional space, we can model also the independence of that, and the independence is very simple. Signals should be kept independent if they have no relationship whatsoever, so there's no redundancy in there. And this you can represent with a prior which is completely flat. If you have a completely flat prior, multiply that with your likelihood, you end up basically with exactly the same as a result, so that would be independence. The nice thing, and that brings me to the learning study that we have done, is that of course you can also then represent something in between. So you could see whatever this as a continuum going from independence to the fusion case here. And that was the question that we had in one of the study. If we start with two sensory signals which are normally independent, by artificially creating a redundancy, namely making them correlate by one another, could we introduce that people learn this redundancy and therefore integrate the signals? So we went back to our little setup here, where we can see and feel object, create these conflicts, and we choose two-dimension, which we hoped were integrated in the first place. Namely, we picked the luminance of an object, so how bright it was, and its stiffness, so you could feel it and it had some stiffness. So a little cube here that you could poke, and it had some stiffness and luminance. And of course, they are not related in the world normally, and therefore you shouldn't integrate them. But then we put you in a situation where for over an hour or so you were always playing with objects where when they were bright, they were hard, when they were dark, they were very soft, and we wondered what consequences it would have for your discrimination performance. We again did a sort of discrimination task, but the task we did this time, we couldn't ask for any dimension like size, so that it doesn't exist yet. So we had to come up with a slightly different task. The task that we came up with is a so-called oddity task. So in this paradigm, you're presented always with three examples of the stimulus, two of which are identical, that's the standard by definition, and one is the odd man out, so it's different from the other two, and your task is simply to tell which is the odd man out. This has consequences if you're not integrating on your discrimination performance. That looks like this. The discrimination would be completely symmetrical if the things are independent, and if they are fused, you're actually losing one dimension, and therefore you get worse in this direction. That's a little bit hard to grasp, so I've tried to get at that step by step in the model that I've just shown you. Get a little space here. So let's see, this is your standard object that appears twice. This is your comparison object, which appears only once. Does anyone have a laser pointer? I think the battery of that one's dying. Appears only once, and of course, if you're in the independent case, thank you. Independent case, then the prior wouldn't have any effect, so your percept would be determined exactly the same as the likelihood. So there's a big distance between those, so those should be easy to discriminate amongst. This way around. Now, if I bring this stimulus closer, at some point, of course, you have a hard time telling them apart, and then you can't discriminate them anymore. The same happens if you present a stimulus on this diagonal axis. At this point, you can probably tell them apart. If I bring them closer, you can't tell them apart anymore. So there's a discrimination threshold which is around here, and since everything is symmetrical, it will be on a circular shape. It will look like that. Now, if you look at the integration case, the picture is completely different. Now, here's my standard stimulus and my comparison stimulus. Due to integration, they will fall together. This one here is merged down on this diagonal axis by integration. And they're sitting on the diagonal already, so it will stay on the diagonal. So, no matter how close I bring this one, you will not be able to tell apart what comes from this diagonal line. Of course, if I bring something from the diagonal line which is the dimension of that you have just learned, this one here you can easily discriminate from this one. If I bring it closer, there's a discrimination threshold at some point. So your discrimination shape in the fusion case will look like that. And then the intermediate case, of course, will be some elliptical shape that looks like that. So in our learning experiment, what we hope to find is if we look at discrimination along the positive and the negative diagonal, that at the beginning they are exactly the same because it's spherical, and then due to learning we would get some asymmetry in there, so that if it comes on the negative diagonal, it should be worse than from the positive diagonal. Okay, that's the experiment we did. So we did the pre-test where we hope it's not integrated, so therefore the same, and then in the post-test after you've trained and the objects are only coming from this diagonal line, that you get this asymmetry. Here's the discrimination curves, how they look like. This is at the beginning, and here's our prediction already fulfilled. You can't tell that there's a blue and a red one because they're exactly on top of each other. So at the beginning, those two dimensions are completely independent, and therefore you don't integrate them. After training, however, we find this nice difference between the shapes, namely that the red one, which is on the negative diagonal, incongruent, becomes wider than the blue one. And that holds true if I plot the average over our, I think, 8 or 9 subjects that we have, that at the beginning they were exactly the same, and at the end we get this nice offset. It's a very small offset, but you have to consider that it's only like an hour of learning or something like that, and you have probably 30 years of experience with the objects that are bright or not. So learning is relatively slow probably, but it certainly occurs, and it occurs systematically. You at best can see if here this is an individual subject, and I don't know, I said 8 out of the 9 subjects learned in the predicted direction that we have. So we really have shown that there's some learning that can occur once you're in an environment where the statistics change so that there's a correlation in there. Humans will use that, they will exploit it, and at the end make discrimination performance, which given the task that we are, make them actually worse. But in general, because you're losing one dimension, so to say, by integration, but has the benefit that discrimination in general should be more reliable. Okay, what I want to show you next is that, or what I want to claim is that this here is a very artificial case, that you basically have a prior sitting on this diagonal which has no variance. And that's probably something that Jeroen would agree with, that normally he has shown that we're living with these bias all the time, and of course that's introducing variance in this estimate of whether or not it's redundant. Here's just a couple of more examples from size estimation. So if you look at the object and you feel it, this would be if there's no conflict between them, but there's so many cases in the world where conflicts naturally occur. Like for example, if I grip and I have a slight mismatch and suddenly the haptically felt shape is slightly bigger than the visually felt shape, that's a very asymmetric, unsystematic case, but I also may feel something with a glove on top that feels bigger than it looks like. Or I have some glasses, the world with my glasses look bigger. If I take them on and off, the world changes simply by changing the glasses slightly back and forth. The size of the visual object changes all the time. So we cannot take for granted that you know this matching between that perfectly. There's always some uncertainty in there. As a distribution, so it wouldn't look like this but it would probably look more something like this. So the intermediate case of integration is more the rule than the exception. Okay, also what Jeroen already got at slightly is the question, what happens if conflicts like that persist over some time? I would somehow disagree with Jeroen that there's no recalibration or that it's not necessary. I think there are many examples that you find recalibration process, and I'll just show you one of them. What happens if you have, like, in the situation where you have glasses on, that you get some sensory motor recalibration. And that's a phenomenon studied, probably most of you know that, very early on from Hermann von Helmholtz, who put on prism glasses, looked at pointing behavior and looked how you adapt to these situations. If you don't know it, I'll briefly sketch what this experiment would look like. So here's your target that you're having, you're looking at it, and your task is to do a speeded movement to it, so you don't do any online correction, it's all pre-programmed, all feed forward. And what is happening then is, well, if you repeat it over and over, is that you're not perfect, you will find some noise in your trials, and may look something like this, exaggerated. Then the experimental manipulation that you do is that you put on this pair of glasses, which shifts the world virtually over here. At the beginning, of course, you have to point there, you have no other information, so you'll land up at this virtual position, you realize that you made a mistake, and then you correct over the time and go back to the real target again. The characteristic is then, if you take off these glasses, you get a negative after effect, meaning that if you take off the glasses, you will point towards the opposite size. And also this miscalibration then gets recalibrated back to the center. So a characteristic learning curve in this prism adaptation paradigm will look like this. You measure the baseline, put on the pair of glasses, you get an adaptation. You take away the glasses and you get the after effect. What is striking is, as I told you, these studies are over 100, 150 years old, and there are tons of studies on this paradigm, that there's really no good computational model out there that could describe this learning process very well, especially the learning rate. You find this here in the sensory motor domain, and if I've illustrated that's happening with a couple of trials, so whatever 10, 12 trials you adapted. There are other examples in the audio-visual domain, for example, if you put in a constant conflict, also that they adapt towards each other. There it may be much slower, that it will take probably an hour or something like that. Even within the visual domain, there are examples like if you put on only a magnifier in front of one eye, what that has an effect that affects your stereo vision. So everything, if you put a magnifier in front of one eye, everything that's frontoparallel will look like it's slanted. Of course, that's only in stereo effect. In perspective drawing, which is another depth view, that is not much affected by putting a magnifier in front of one eye. So you can create conflicts in the visual domain, and also these are getting recalibrated. But that takes up to days. So we did an experiment, or Marty Banks did an experiment with Wendy Adams, where they had people run around for over a week with these funny glasses, and they could report this recalibration effects happening within 2 or 3 days or so. Okay, so the question is why these different learning rates? And in order to understand that, I think you have to consider the situation a little bit more carefully that you're in. So consider you have just done this pointing movement, you realize that you made an error, then the question that your brain must have is, what's the source of the error? Where does it come from? And in principle, there are 2 possible ways where the error may come from, namely that you made a wrong prediction or you sent out a wrong motor command, in which case it would be a systematic error of the model that you're having to send out a motor command. And since it's a systematic error, that's the one you want to correct for. But on the other hand, there's measurement noise, there's noise in the system. So it may be a simple random perturbation that you had in this one moment in time, and then of course it's the random error, you don't want to correct for it. So here are opposing effects to those. This one you don't want to correct, this one you want to correct. Both of these estimates, so to say, have uncertainty. Your prediction, whether or not you made a right or wrong prediction, has uncertainty associated with this, indicated by this Gaussian here. And also your measurement noise, of course, has uncertainty associated with it. With this, the situation is very similar to the integration process. Maybe what you should do is you should take estimates and you should combine them again in a weighted fashion, and that gives you the best optimal estimate of the current conflict that exists out there. And of course, since we do pointing movement, in this case it is a recurrent process, and the more engineering people amongst you will then realize that it's a very simple form of Kalman filter that you're doing there. And you can express then the learning rate basically as this Kalman gain, where you can see that both noise sources, that of the prediction, and that of the measurement is in there. And that's the experiment that we want to do next. We want to vary the noises that is in the measurement and the noises that is in the prediction and see whether it has predicted effects on the adaptation rate. Okay, what effects should it have? In order to do this, again, a cartoon-like drawing of what the situation is. So imagine you've pointed for a number of trials, there's noise in your pointing movement. Of course, now you see the target. You can make a feed-forward prediction of what your motor command should be. And you ended up somewhere, and you have a measurement error here. And as both are uncertain, you do the weighted average, and that's the amount you correct on these trials, which is indicated here by the screen line. Now, the manipulation experimentally that we can easily do is we can make the measurements that you're getting more noisy by simply blurring the visual display. What should happen in that case is you shouldn't trust your measurement anymore, or not as much, so the weighting should go down. In this case, you would correct your state less on every draw. Of course, it has an effect that the adaptation rate would slow down. In essence, that makes logical sense. If you have a hard time detecting that there's an error, you should adapt more slowly. That's basically what that is saying. Okay, you can easily do this experiment. We didn't do this with a real pointing task because then you see your hands and so on, and this gives you information. We did this in front of a large virtual screen, and the hands were covered underneath a cloth. And the feedback that you're getting was one of those Gaussian blobs on a back projection screen. And it's hard to see here, but it was either a relatively good to localize point. Still, it was hard to see, but it was good to localize. And we can measure psychophysically how easy it is to localize. It's a 4-degree little blob, or we made it really large. It's almost the size of the entire field here, 48 degrees, like a Ganzfeld almost. That is really hard to localize. So the prediction would be here you adapt quickly, here you adapt slowly, and that's exactly what you find here in these learning curves. If the size of the blob is small, so feedback has relatively good certainty, you adapt quickly. If you are very uncertain, you adapt much slowly. It's also present back here, but that's harder to see because everything is blown on top of each other. Okay, probably the more interesting manipulation we did then is to measure, basically put noise in your feed-forward model that you can have. And the way we did this is by basically perturbing on every trial the mapping that you had of the world. The way you can do this is basically, literally spoken, you get a new pair of classes every trial. Of course, computer generated, not real classes. But you keep on the old one. So what you get here is like of this state, like a random walk kind of profile. As a consequence, you can still make a forward prediction, but this forward prediction would have more uncertainty. So you make the forward prediction, has more uncertainty, you get your measurement. If this is more uncertain, you should trust your measurement more, and therefore you should correct more on every trial. So as a consequence of having an uncertainty in the feed-forward model, you should adapt more quickly. And that's exactly the experiment that we have done. Here is the adaptation profile for a world that's relatively stationary, and now comes an adaptation profile when we perturb the world so it's less predictable, and you get a nice speed up in the recalibration profile as we would have predicted. So as a consequence, we concluded from that study that the adaptation rate depends first on the reliability, as I've shown. If that's unreliable, you adapt slow. And the adaptation rate also depends on the uncertainty in predicting the world. And if that is uncertain, then you should adapt more quickly. So at least as a first approximation, such a simple kind of Kalman filter model is a good predictor for human performance. I will emphasize that it's a first approximation because the human, of course, has a much harder task to do than the simple Kalman filter has. The simple Kalman filter is given all the noise sources. The human, as we've shown, learns those over time, and that's not all in this model here. And that's the next step we want to look at, is how the human actually learns these different uncertainties and noise sources, especially that quickly, so that the experience that the user had before we measured the adaptation was only like 50 draws. So it's amazing how quickly actually you learn such new statistics and pick them up. In a way that probably also predicts the different adaptation rate that you find across modalities, because I would argue that in the visual motor domain, recalibrations, the world is so much more unstable than in the visual domain itself. Within the visual domain, it rarely occurs that I have a magnifier in front of one eye only, and therefore mass stereo and texture or perspective so up. Therefore, it's an unexpected event, and therefore you should adapt very slowly. Whereas in the visual motor domain, as I've showed you some examples here, it occurs more often. But a major reason why I believe it occurs even more often is the reason that we use tools If we use tools, and we don't want to do this in a closed loop fashion that we visually control where we go, and we want to use it in open loop, we have to have a new calibration in our sensory motor loop every time we use a new tool. So we have to do this very, very quickly. And that's why I believe in the visual motor domain it happens quickly, because there's lots of uncertainty in this in the world, whereas in other domains there's less uncertainty there. Okay, I want to briefly just make the link back to the integration model that I've shown you, and show you how this adaptation model very nicely fits into the same kind of scheme. So I'm basically redrawing what I've showed you just a couple of slides ago, namely the model. Now the measurement is up here, it's not down here in the corner anymore, and it has different amounts of noise, but that's just a matter here. You have your prior, which is, in this case, this is the measurement uncertainty related to the adaptation file. This is your process noise, or your noise in the feed-forward model, in the prior. If you do the integration process, that's where you ended up with. And basically what it says in integration is, this tells you how much the system believes part of this noise is then discounted by this bias. But there's a bias remaining on every trial, which is the offset from the diagonal. So this one would be the best current estimate of the bias that you're having, and this part would be the best current estimate of the noise in the system, given by that. So recalibration, of course, wants to get rid of the bias, so what you need to do is basically, in the next step, take away this amount of bias. Now, since we're living in a two-dimensional world, it's hard to say where is the bias, is it in the visual or is it in the haptic domain, so you need to do an additional step. Namely, you need to know if this is the, now we go in the bias space, so the bias line is ambiguous whether it's in the visual or in the auditory domain, or haptic domain, but it's somewhere offset. There's nothing in the signal that could tell you where the bias is, whether it's in on the visual side or whether it's in the haptic side. So again, what you have to use in this case is a prior information that you may have gained through experience over the last 30 years that you've lived, or 50 or 40 or whatever. And this prior may look something like that. In this example I've drawn here, it would be that I believe that the haptic modality is more likely to contain a bias than the visual one. And if I multiply those two distributions again, I get the optimal estimate of what I think, how much of the bias, or all bias that I have, is due to vision and how much is due to haptics. And then I take this error and go into the next step and correct my prior based on this estimate. And this I do recursively, and at the end I end up with a calibrated state. So the integration model and the recalibration process is more or less the same kind of model that we can describe that. Okay, so it somehow probably seemed that these biases are something that may be artificial by putting on glasses or gloves or whatever. But what I want to show next is a couple, or is one study, that such biases of course occur very natural in everyday life, and the system seems to calibrate for that continuously. We didn't start the study that I want to show you now directly with this question, but we started from a slightly different angle. And the reason for why starting from a slightly different angle was that a German TV show came to us about 3-4 years ago from the WDR called Kopfball, and it's like Mythbusters or so. And they came to us with the question whether it's really true if you're lost in the desert that you run in circles. And I, at the end, come back and what that has to do with the integration and recalibration process. So we said, well, I have no idea why that is, but if you want, I can look up in the literature. That's when we just started some stuff on walking at that point. But so I was surprised we didn't really find any literature on that kind of topic. What we found is a lot of anecdotes. If you look in the literature, you find from whatever Mark Twain to Tolstoy, you find stories about people getting lost and run in circles. There are much more, for example, Laurel and Hardy, and there's even comic drawings on that, and anecdotes. So it's a wide belief that that's really going on. But there's nothing really in the literature. So the TV station was really nice. They said, well, okay, then we don't make a 5-minute plot on that. We give you some time and you do the research for us and then you give us the story. So they paid us for going down to the desert in Tunisia down here. That looked something like that. It was actually not easy to find a spot which is even in the desert completely homogeneous, where you don't see a palm tree or some other thing, a landmark in the distance. That, of course, then it would be boring if you have that. So we were searching around for quite some while until we found something like this environment, which was a little bit of hilly, so you didn't see the horizon always, but the sand dunes weren't big enough so that you would die, basically. But the task was very simple, so we asked people, we gave them a direction. I said, here, walk for 4 hours in that direction. The slight problem was that it was 45 degrees, and they didn't have any navigation. We gave them some water. And, well, we didn't give them a GPS, but there was a person also for security walking behind them with a GPS, and we recorded their path. And somewhat to our surprise, we didn't really find a circling behavior here. So the person here was started out in this direction. He was had to go straight. Up here was we said is the camp somewhere. So at the beginning, in the first half an hour to hour or so, he made a nice curve of, you can see the scale here, that's a kilometer, so that's roughly 12 kilometers the entire path, roughly 4 hours. He made a nice turn in the first half an hour to an hour or so, but then he walked more or less straight. Here the dot is where he made half an hour break and had some water. So that was okay. So we had the next person walk, and also he was set up here, should go down here. He made a more or less straight pass, a little bit wiggly. So didn't really seem like circling behavior. And then we had a third person walking out here, and it's in blue because that was at night then. And at the beginning there was a nice full moon visible until there was clouds coming, and the clouds basically occluded the moon, and then he started to do something like a circling behavior. So there may be something to it. So the first intuition, of course, is that, well, it has to do that you, especially those people where it came from the camera team, so they were used to the question, they were thinking about the question a long time, so they were probably just using the sun. So that's more or less trivial. The problem is we couldn't really do controlled experiments here because then a sandstorm came that looked like that, and also the natives there told us we have to get out immediately. So we only have these 3 subjects really here in the desert. So we got out as quickly as possible. Well, results are circuits are so not inevitable certainly, but it may probably have to do with the sun and moon, and there's still some absolute cues that you at least have if you have a cognitive strategy that you can use. So we wanted to get at it a little bit more thoroughly, scientifically, even so still not perfectly controlled, but we found a little forest. Here's Tübingen, where I am. Here's a forest near Karlsruhe called the Bienwald, which is not too dense, but also dense enough so they don't have a long distance view. It's relatively flat, and we gave them the same task. The only thing that we varied here is, or what we recorded, is the days when they were sunny and when they were cloudy. And here's the interesting thing: if you walk on a cloudy day in the forest, there's a nice circling behavior happening. And here's all the people on a cloudy day, nice wiggly circling behavior. Here we had 2 people who walked in a sunny day, and you can see they're going more or less straight. Here there was still a cloud at the beginning for this one, but it was more or less straight. This person even left the forest, we had to turn him around and send him back in. Probably surprising if you use the sun is, again, this is roughly 4 hours of walking. And what we draw here in the arrows is basically the shadows that the sun would produce, or the direction of the sun. In 4 hours the sun moves, of course. And if you would predict, you would only be using the sun, you would actually predict a more curved path than people are doing. Why they can compensate for the movement of the sun is still a puzzle to us. It's probably something we want to get at in some of the further studies. But certainly in the animal literature that's known that animals can correct for the movement of the sun in navigation tasks. So there certainly seems to be something that, well, the visual information plays certainly a critical role whether or not you walk in circles. But why do you walk in circles? And we wanted to understand that. And since vision played a role and made you walk more straight, we thought, well, take out vision completely, blindfolded people, and let them run blindfolded. Of course, that in the forest is not the best idea because you hit the trees, so we had to find another environment. So what we found here as an environment was a nice sand island in Holland called Vlieland, which is 3 by 6 kilometers long, completely flat. The only downside it has that the Dutch military is using that as a drop zone for bombs and they're training. And you occasionally find these kind of things lying down there, but they guarantee that it's safe to walk there. And it's open for the public on the weekend. So we took this person, blindfolded her, more than one, and gave her a GPS and then said, no, walk straight. And the interesting thing here was what's happening. Now you can look at the scale. That's again meters, so this is 100 meters. Here she started, and immediately she started running in circles. And the diameter of the circles here are something like 15 meters, so that easily fits into this room here. And this person is thinking she's going straight. And that's even more surprising since there's still, at least if you would be used to it, enough cues, because you're on an island, there's wind coming. Even so we put in earplugs, you still could somehow hear the sea a little bit. So you could be using, in principle, those cues, but they somehow don't help you. This person even said, it's strange today that the wind is constantly changing direction. Okay, so there's certainly circling behavior in our system. So where does that come from? Well, one of the predominant ideas, if you naively ask people, is that it has to do with body asymmetry, that one leg is stronger than the other, or longer, or something like that. There's some experiment, well, we did a lot of experiments by artificially introducing asymmetries, but I think the most convincing argument is that if you ask people, and this is now back in Tübingen, on an airstrip, so we only could let them walk for like 10 minutes in a row, and we had to stop them, take them out, that you find people who are often walking in one direction, but then they turn around and walk in the other direction. So there's not very systematic path if you look at it over a longer time. So they sometimes go to the left and sometimes to the right. There are some extreme cases like this. This person is always going to the left here on this stay that we had. But this person, KS, if I go back quickly, was also, was also running in the forest, and there he was running exactly in the opposite direction. So even these extreme cases walk sometimes to the left and sometimes to the right in the circling behavior. So it certainly seems that it doesn't come from any body asymmetry, so it must be some perceptual effect that is going on. If you look at the distribution of curvatures that you're having, you find that overall there's almost no bias, it's at 0. Of course there's deviation that makes them sometimes go to the left, sometimes go to the right, this deviation. There's a few extreme cases which, when we have measured them at least, they are going systematically to the left or systematically to the right. So what is that? So the reason why we think that is going on is very simple. If we take away all absolute cues, we only have relative cues. The only source of direction basically we're having is given by our vestibular organ, by our, from our balance. And what that organ does is it sends us acceleration. In order to get a direction from an accelerometer, all technical people will know that if you want to get a position from an accelerometer, over time it gets drift. And this drift is basically what is going on. So the model that we have for the circling behavior is very simple. So you have on every step, so we make it discrete here, this model, on every step you have an estimate of where straight ahead is, and this estimate is noisy. It comes from your vestibular organ and gets updated every step, the way we do it. So let's say it is noisy and this way it points slightly to the left. So the next step you're going slightly, follow your sense of what straight ahead is. Then you get another sample of your noise. It probably goes in the same direction at this moment, and that walks you more and then may go back, but that brings you on a curved path if that's a relatively slow process. This is now simulated data, which looks pretty much the same as the data that we have found experimentally, with such a very simple model, you can produce this kind of circling behavior. And as I said, what that basically is simply a random walk which comes from the integration of a noisy variable, which makes you, in this case, if this is the curvature, goes to the left, then it goes down. Here it makes this circles to the right, then it goes up again, more straight, and then it goes down again, makes you go in a curve to the left again. So such a simple model can explain this kind of circling behavior. And the parameters that we use for that are pretty much what physiologically is plausible. Okay, so now I come back to the recalibration idea. What I've said, normally, of course, we don't run without vision, we have vision available. And luckily, in these trials where we let them run, we had conditions where we took off the glasses so you could see the world again. So the prediction would be, if you really have an unbiased estimator for what the sense of direction is, if you get vision, then you can reset it to 0. So basically what we look at is, you come onto a stop here with some curvature, and then at the end you should go more straight. So we look basically at the correlation between the curvature before and the difference between curvature from before and after. And what we find here is a nice correlation between those two, which is a sign of a recalibration process that comes in once you turn vision on for that. We had two different kinds of the blue and the red ones, if you wonder. We had two different kinds of stops. The one stop in red is really when they had vision available. We took off the glasses, they had vision available, they were moved to a new stop and they could go. The blue dots here are, sometimes they were leaving the field that we're giving them because there was a tree or so we had to take them at the shoulders and redirect them. And it seems like this haptic information is enough to reset your sense of direction. It's not as much as if you take vision off. So vision off is basically almost perfect recalibration if you look at that, but there's certainly a nice correlation there also for those when the vision is not available, you get other absolute sources of direction. Okay, so what this study basically shows is that such recalibration processes are constantly going on in order to recalibrate them. And that's probably something where I disagree with your room, and I think still have to find out where the differences are, why he can claim that sometimes you get miscalibrated systems. That's probably something for the discussion later on. Okay, as I've also shown, now a few fun slides probably, is that it's really hard to do these experiments in real world environments. So often what we do is we want to do this in laboratory environments, like we did for vision and haptics, where we use little robots. So in order to do locomotion studies, at least in large field like we had in the desert or so, if you want to do this in a lab environment, you need some sort of a treadmill. So we recently came up with a European project, got a few engineers together, and we had the idea to build a treadmill, but a treadmill that goes in both directions, omnidirectional treadmill. When we started the project in 2005, I think it was me and Heinrich Bilthoff and Karl Goetz who had the idea to build something like this. So it was a big treadmill made out of balls where there's one treadmill running and actuating these balls, which is sitting on a turntable. This way you would have a two-dimensional treadmill looking like this one here. And we thought that's a good idea to implement something like that. And our colleagues from the Technical University of Munich, Martin Schweiger, and they implemented it for us in a small scale. And here you can see how that works. So here's the grid of balls. Here is a toy human walking on it. Here you see the treadmill rotating underneath and always bringing this car back to the center so it doesn't escape here. So it works in principle quite nicely. It worked for humans, also a little bit small scale. The big problem is, of course, we want to have it much bigger to walk on it. And the problem is in scaling it, the whole thing up. The problem is you can't take many more, or you can't make the balls much bigger because you get an unstable ground. So the balls are relatively small. These are already 5,000 balls or something like that. If you want to have something like a 4x4 active area, you would need millions of balls, and the grid isn't big enough and it has a lot of friction. So Martin Schweiger, who's the guy from the Technical University of Munich, did his PhD on this project with us. He came up with a different design, which is so-called Chaw's treadmill. It was originally invented from Iri Iwata in Japan, but never brought really to a setup that was really usable environment. So we scaled it up quite a bit. So this is now 6 by 6 meters here. That's almost to scale this guy here. But it was made out of belts going in this direction, and then a big chain out of the 25 belts which run in this direction. This way we have an omnidirectional actuation again. And that is now in Tübingen available, and it works. So here is Jan Soman, a postdoc in my lab, who did the human side of this project. And of course what you need is you need to know the position on the treadmill. That's why we have this funny tracking system and the funny helmet on. You look at the virtual world through this lenses, but you can walk on this treadmill basically in any direction that you want. And since we have a large size, the forces that are acting on the body are kept to a minimum. The thing is quite a monster. It weighs 12 tons, and the moving mass is 8 tons that is around, so there's quite some big motors behind it. But it's, I think, the first workable omnidirectional treadmill where we can now do psychophysical experiments, and we don't have to go into desert. So that was much fun to do. Okay. That brings me to the last experiment I want to show you. I've shown you that they constantly recalibrate. The last question we wanted to address is whether there's really an automatic process, whether you need to detect conflict consciously or actively in order to recalibrate. And in order to get at that question, we went back to a design. Also, we did this study together with Ben Bacchus, but to a paper that Ben Bacchus published in 2006, where he looked at learning of new cues. And the paradigm he used is based on this Necker cube. I guess most of you know this Necker cube, that you can see it in one of two ways, either with this side in front or with this side in front, and it alternates back and forth when you look at it. If you put it in rotation, it will, I don't know, some people will see it rotating this way. Who sees it rotating this way? Some people will see it rotating this way. Anyone seeing this way? Only a few. Yeah, you have a large bias in one direction, depending on the... But you can see it flip rotating as well, the same way as you can see it flip in depth. Depending on the depth, or it rotates one way or the other. Of course, you can disambiguate the whole situation by putting on a stick through it or other depth cues, and then you have a non-ambiguous Necker cube. And he used exactly this, but he associated two cues. In his case, it was the location where the object was presented. If the Necker cube, well, at the beginning, it doesn't matter. You can present the Necker cube somewhere up in the visual field or down in the visual field. You will always see it alternating back and forth. But then he trained subject with a disambiguated version of that thing. In the upper visual field, it was rotating to the left. In the lower visual field, it was rotating to the right. And you do this for an hour or so. And then afterwards, you get some effect that whenever you present an object on the upper visual field, you see it consistently rotating with this contingency to the right, and here to the left, and here to the right. The problem with this study, and why we redid it and looked at the automaticity, is that of course you can clearly see that something is up or low in your visual field. So you can clearly see this additional cue. So what we wanted to come up with is whether we can find a cue that is not visible. So you can exclude basically all explanation about attention or consciousness or whatever. So we want to come up with an invisible visual cue that we can train people with. So what is an invisible visual cue? First of all, well, we changed the design a little bit. We went away from the Necker cube to the rotating cylinders, but it's the same thing. You can, if these lines move up and down, you can see a cylinder moving this way or the other way around. And we can also disambiguate it using other depth cues to it. Now, the invisible cue that we are using is something that naturally occurs, namely that we make the image of one eye slightly bigger than the image of the other eye. That naturally occurs. It's called vertical disparities. If an object is closer to one eye, The image projected in the eye is slightly bigger than to the other eye. So that's a vertical disparity. But that doesn't have any effect perceptually. And we're trying to prove that, or we prove that you can't see this kind of cue by doing an experiment. Or here you see the stimulus, how it looked for real, ambiguous, rotating cylinder, and then this ambiguous, probably hard to see here. The way we prove that you don't see it, again, we did an oddity task that I've showed you before. So we showed 3 examples in 3 different intervals, one after the other, and we changed the polarity of the vertical disparities. Once it was in the left eye smaller than the right eye, and twice it was bigger there. And people simply had to say which of the intervals is different on any sort, whether they see some funny depth or whether they see some whatever funny thing, they should tell us. But it's basically impossible. They don't see anything. It's basically chance level here is 33%, there's 3 intervals, so they don't see anything. Even if we explain them what the cue is, that it has to do about sizes of the eye, and one eye image is bigger than that. So in principle, if you close one eye and the other one, you could easily do the task. You could show it. But even if you explain everything, at least at 2%, people are hopeless and they can't see it. So we used this 2% of vertical magnification in one of the eyes, and we correlated this one with the rotation direction of our cylinder. Made this contingent in training, and then in a test similar like what Ben and Bacchus did, we presented the ambiguous version of it and hoped that our new cue, namely the size, relative size in the 2 eyes, has an effect on the rotation direction. That's the trials, so we have learning trials and interleaved test trials. I wrote here if they wouldn't work, so this is exactly the learning curve that you find here. So over whatever 80 trials or something like that, you get a nice effect of this invisible cue that gives you training. That also persists after 2 minutes. We do this, so it's not a short-term adaptation effect or something like that. It persists for quite some time after the experiment is done. That's a study actually just came out yesterday. Okay, that brings me to the conclusion. It's exactly 1 hour. So let me quickly summarize what I wanted to show you here. First, I started with that the brain takes all the information that it has and integrates that in a statistical optimal way, taking the variance of the signals into account. The brain can automatically learn these redundancies in the world. If signals are made in correlation, the brain picks these statistics up and starts exploiting this redundancy in the information in order to get a more reliable estimate at the end. When the signals are biased over a persistent time, then the brain recalibrates these estimates, and such a process can be well described using a Kalman filter process approach, which is basically exactly the same as the integration. So it's all one framework. What I've shown you in the last 2 experiments is that also these biases occur very naturally, like in the circling behavior that we found, but they are also automatically picked up, even for signals that you are not even aware of, that you can't see. Not even if you try to see them, you can't see them. Okay, so of course, as everyone else here, I haven't done these studies alone. There's many people in my lab who has done that. Here the locomotion stuff, he did the last learning study, Massimiliano. With Marty Banks, I did my postdoc. The recalibration study in the Kalman filter was done with Johannes Birch. Benjamin Bacchus was also involved in this last study. And of course, lots of funding sources available. So, thank you very much.